So we're going to leave off, or where we left off last time. We see that, and we're going to start moving in on talking about cool stuff about this. Okay, and one of the things that I want to talk about is how I1 and I3, I'm sorry, I2 and I3, I've circled them there. Those two, if you add them together, you're going to get your total I current, which is equal to I1. So I1 equals I2 plus I3. So if you need to go back, that's what that looks like, and why. And if you notice in the big box that we've got all the values listed, I1 is 2.3, I2 is 1.28, and I3 is 1.02. If you add those things all together, you get 2.3. So I2 plus I3 equals I1. And I sort of prove it there. Now, you could do something clever and instead for I3, instead of saying, oh, well, let's, instead of doing VP 5.1 divided by 5.0, I'm going to say, oh, no, I would rather say I3 is equal to I1 minus I2. You could do that, but here's what I would recommend. Don't. Stay with I3 and stay with Ohm's law, okay? So do step number 4 the way step number 4 was laid out for you there. You can use this I total equals I1 equals I2 plus I3. You can use that as a check, okay? Because if that doesn't work out, then you've done something wrong. So let's talk about problem solving. In these situations, we've got the first thing you do is draw your diagram. Okay, hopefully you guys have noticed that I drew my diagrams. Secondly, we put all of our knowns and unknowns off to the side, and we identify the main goal. Okay, so let's go back a little bit. What was our main goal? Our main goal was to, in that circled, black circled I1, I2, I3, that was our main goal. We wanted to know the current through all three things. Break it up into pieces. Okay, so we broke up the parallel parts and the series parts, and we're using V equals IR, Ohm's law, to find all the pieces that we broke up. We also need to use care, or be very careful, when we're doing 1 over C EQS for capacitance and 1 over R EQP for resistivity or resistance. You have to, okay? So I know you can do it quick on your calculator. Just make sure that you do that final inversion, okay? If you don't invert that final equation, you're in trouble. Then you got to ask yourself in the end, do the C equivalents and the R equivalents make sense? Okay. And for that matter, not just the series for capacitors, but the parallel for capacitors and vice versa for the resistances. You want to make sure that they make sense. And if they don't, then that's your first step into a problem. Okay. So you're going to get the wrong currents if you don't have the right resistances. Okay, so here we're going to talk about the electromotive force. All right. It's first of all, what's the first thing that we're going to say about the electromotive force? Not a force. I wish it was a force. No, I'm just kidding. I don't know anything about it other than in the 1800s, they thought it's forcing current through, right? So something is causing this force, and they called it an electromotive force, okay? but not a force. All right, it's just a potential voltage, a voltage potential. Potential and voltage are synonymous, so it's a potential that moves electrons. Okay, and we call it EMF or capital EMF. And here's how it breaks down. So we've got our copper top battery, as they say in the Matrix, and that is equivalent to the schematic. So the schematic here has a battery with an internal resistance, and we're calling all the internal resistances R, little r, small case r, because it should be a small internal resistance. Okay, so our internal resistance is a small r. We've got our voltage across the actual driving electromagnetic force. This is just a schematic, okay, because we can't do the chemical. Each chemical in there is doing its thing in the battery, and we can't go to each one of them and say, okay, I want to take you and put you over here and add you up, but you're over here, your resistance and blah, blah, blah. I don't know. We can't do that. So we separate them. We take the electromotive force and we put that in our diagram as the source or the battery. Then we put the internal resistance as our resistance, R, little r, and we show that there's some current. Okay, so that curly Q E, that is the symbol for the electromotive force. And just so you know, of course, it's a voltage, right? The units of it are voltage. So then we have equation 21.44 in the book. And 21.44 has our terminal voltage, which is what we used to call our straight up voltage. But now it's our terminal voltage because we're working with the electromotive force, EMF. So we've got E, and if we subtract off the current times the internal resistance, the current going through the battery and the internal resistance, if we subtract that off, we get what we have as a terminal voltage, the voltage at the terminals. Now, if we were able somehow to take something and measure the voltage directly without having any current flow, so the current is going to be zero flowing through the battery. If we could do that, then our terminal voltage would be the electromotive force, the EMF, okay? But we cannot, right? We don't measure. Voltage is a calculated thing. What is measurable, however, is current. We measure the current, and if we have a well-known resistance, we can say, oh, I measure current, I have a resistance, and because V equals IR, I find out what that terminal voltage is. So that can't happen, and since it can't happen, we don't even look at Vt equals the electromotive force. We just go straight to Vt equals the electromotive force minus the current and the internal resistance times the internal resistance. So let's look at a large truck and a motorcycle. A large truck and a motorcycle both have batteries of 12 volts. The truck's battery, however, is a lot larger than the motorcycle's battery. So the battery of the truck is large Q. The battery of the motorcycle is a small q. And the larger the battery, the smaller the internal resistance. And I'm going to show you why that is in a minute or two, okay? So let's look at another circuit. Here's the basic circuit for a battery, which used to be where the E is. It used to be just that, but now we've got the E, and it was called a voltage, overall voltage. But now we've got the R, internal resistance, the electromotive force, and we've got our RL for load, and then there's a current that's going to go all the way around. So, of course, V equals IR, and that's where we start, but instead of V, it's our electromotive force, curly E, equals I REQ. What is the REQ? Well, that's just the internal resistance plus the resistance of the load, okay, so RL. So since the electromagnetic force, EMF, is equal to I times R plus RL, and we can solve that for I, and that gives us equation 21.45 in the book. I equals EMF divided by R plus RL. So let's do example 21.4, and I'm gonna get us to this point here. Let's back up just a little bit. We're gonna do part A. Okay. So example 21.4. We're given that for the battery, the EMF is 12.0 volts. The internal resistance is 0.1 ohms. What is the VT? Okay, so VT, we're going to go back and write in VT equals, of course, EMF minus our current times our internal resistance. We just don't know what that current is. We're also given that the load is 10 ohms. So we know what the load is. We know what the EMF is. We know what R is. So we can take 21.45 and the one right there, the boxed in equation at the top there, we can take that and figure out what our current is. And it turns out if you do that, 12 divided by 10.1, you get your 1.19 amps. So now we can then use the equation VT, which is 21.44 in the book. We can use that to figure out what our terminal voltage is. Velocity. 12 minus 1.19 times 0.1 makes 11.9 volts. Okay, so that's how you get your terminal voltage. So let's do B, and here we go. For B, we're changing the load from 10 ohms to 0.5 ohms, so half of an ohm, and we still want to know what the terminal voltage is. Okay, so fine. So let's go on up here to find the current first. So our electromagnetic, our EMF divided by 0.1 plus 0.5 is 0.6. That ends up giving us 20 amps. That is a lot of amps. So then we're going to come back down here a little bit and solve for VT. We've got our 12 volts minus 20 amps times 0.1 ohms. Our VT is 10 volts. Kind of surprising because our VT for 10 amps, or for 10 ohms, is 11.9 volts. It hardly dropped at all. And that was with a larger load, a lot larger load. And so it's kind of weird that with this smaller load, our voltage isn't hanging on as well. Our terminal voltage is definitely dropped off. Okay, so let's talk about that. So with RL of 0.5 ohms, our terminal voltage was far less than our EMF. That is what we call a heavy load, okay? RL equal to 10 ohms, our terminal voltage was 11.9, which is pretty close to, if it's going to be smaller, of course, but it's almost equal to our EMF initially of 12. And so we call that a light load, okay? The heavy load is a no good situation. The light load, of course, is a better situation. And we balance our circuits out so that we don't have circuits that run like that no good situation, right? You don't want to have a heavy load for what you're doing. So how much power do we lose with 0.5 ohms through the load? Okay. So we've got our current of 20 amps. When you're doing power, you want to use the equation I squared, okay, times R load, all right? Because you're trying to look at the loss of power across that one resistor. So you have to figure out what the current is through the resistor, square that current, and multiply it by the resistance of the resistor. Our current is 20 amps. We squared the current, and we're going to get 400 times 0.5 is 200 because it's just half of 400. That's our wattage, okay? That's a lot, you know, but we don't have anything to compare it with until we do it with the, excuse me, till we do it with the other load. If the other load at 10 ohms, we do that, we see that our current was 1.19. We're squaring that, and we're multiplying that by our 10 ohms. That's only 14.16 watts, or 14.2 if you want, watts. And that is quite a bit smaller. If you compare those two, that's a lot less. So part D. Let's say that the internal resistance that was 1.1 ohms goes up. You know, the battery heats up, or who knows what happens as things go. But the internal resistance isn't going to be constant for a battery. We're going to consider it constant in this class, but it's not always constant. This is a situation where it changed, and it went as high as 0.5 ohms. So that's our new, our new internal resistance. So our new internal resistance, we want to do all the same things that we did before, only now we're going to, I'm going to put the two different loads, 10 ohms and 0.5 ohms. I'm going to look for the current through them with this new internal resistance of 0.5 ohms, which happens to be the same as the load on one of them. And the terminal voltage, we're going to look for that, and we're going to look for the power loss across the load. So here's what we get. And I wrote down the equations for each, right? So I is our EMF divided by our new R, which is 0.5 ohms, plus RL, which would be either 10 ohms or 0.5 ohms. That gives you 12 amps for the 0.5 ohm and 1.14 amps for the 10 ohm. So we're already seeing that the amount of current that is needed is far less for the 10 ohm, about a tenth actually. And the terminal voltage hardly drops at all, even though that internal resistance had gone up quite a bit. It went up 5 times. It still didn't hurt hardly the terminal voltage. But for the 0.5 ohm load, it really did. Okay. Then the third thing that we want to know is what is the power. So we went down considerably in our power loss. We didn't lose 200 watts this time. We only lost 72 watts. However, the 10 ohm resistor load only had 13 watts loss of power. So hopefully if you guys go back through and look at these numbers, you'll be able to see, well, and in fact, it's actually example 21.4. So I added to the example a little bit. So play around with that. Make sure that you guys know how to do this. And we can see that even though it is a better balance, we still want to go with the 10 ohm. So my one of the things I want to point out is how circuits are sometimes counterintuitive. You might think that having a lower resistance would be a better thing, and yet it's not. The better balance comes from the 10 ohms. I don't know why I have better balance on the wrong one, but you don't want the 0.5 ohms. That's not a good balance. Okay. Sometimes I get my minus signs mixed up. Okay, so circuits are sometimes counterintuitive, and that is totally true. You think you're getting something, and you're really not. So let's do 2 batteries in a row. We've got E1, R1, E2, R2. It's EMF 1, of course, and E2, R2. And we're going to look at all the same stuff that we did before. I'm not making up these equations. I'm just saying that if they're in series, E1 plus E2 has to equal our current that's flowing through and our times our equivalent resistance for the circuit. We find that our equivalent resistance is R1 plus R2, but the 2 batteries are identical, right? So their internal resistances are the same. So R1 equals R2 equals R. So R1 plus R2 is just 2R. And the batteries are the same. So EMF 1, EMF 2 are equal, and that equals just EMF. So we can then write our equation for the current as 2 times the EMF, because we got 2 batteries, divided by 2 times the internal resistance of each of the batteries, plus our load resistance. Okay, so the blue is just, those aren't really lines, those aren't wires. It's the schematic showing the battery and their equivalent points on the schematic. That's all that is. Okay. So that was batteries in series. What about batteries in parallel? Okay, well, this kind of gets a little bit tricky, and there's a video, auxiliary video or additional video I put in the lecture area. And that fellow does this kind of stuff for a living, literally. And so he teaches a class on it. And he's teaching electricians, okay? And he doesn't deal with the electromotive because he's not a physicist, and we're studying physics, but he's studying electricity. He cares about what works. Anyway, he looks at batteries in parallel and in series, and he talks about how and why when you put two batteries in parallel, you want them to be equivalent. So their EMF has to be equivalent, and their internal resistances have to be equivalent. Okay, there are reasons for that. And if they're not, it's okay. You just need to have a diode in its place. And if you don't have a diode, well, you better find one. If you don't know what one is, because we haven't talked about it, that's too bad, because I don't think we're going to talk about diodes in this class. So just take it that E2 equals EMF2 equals EMF1 equals EMF. And essentially, all you're really doing is doubling up, okay? And do watch that guy's video, because it will show you how you double up the power. You double up your charge delivery. Putting batteries in parallel, there's a definite benefit to it. So you'll want to do that. At any rate, here's one of the things. This is basically what I wanted to show you. If you notice, to get the internal resistances correct, we have to do R internal, 1 over R internal equals 1 over R plus 1 over R. That is equal to 2 over R. So that means when we invert that, we now have R internal equals R over 2. Remember when we were talking about the truck batteries? Well, and the motorcycle battery. The truck battery is essentially this type. All of the batteries are this type, but it's basically saying I've got more than one motorcycle battery in parallel inside my regular battery, truck battery, okay? So the internal resistances go down every single time you put these in parallel, okay? So that's another benefit to having parallel. And if you don't have diodes, just make sure your AA batteries or AAA batteries are all the same. That's it. It's easy to do. Okay. So what else do we have here in this lovely video? I throw on a little bit of stuff. Let's see where we go here. Okay, the voltage drop across E1 and E2 is the same. So that's just me pointing out again, EMF2 equals EMF1 equals EMF. And I've drawn an equivalent circuit in the lower left here. We've got our EMF. We've got our internal resistance that is now no longer R. It's R over 2. We still have our load. And so all I've done is take the batteries that are in parallel and draw them as their equivalent battery. Okay? And in the end, it just ends up being the electromagnetic force over R over, with the internal resistance of R over 2. So, this is where we left off last. That's where we left off last one with, and I'm gonna stop here with this one. Thank you for hanging in there with me and watching this second video on Chapter 21.